Okay, apologize on the glare and a couple points on the board. But let's look at the back wall, the south wall, and let's talk about its reinforcement. What we observe or what's observable doesn't mean it's so, meaning that it's not verified, what I'm about to say, in respect to I only see one piece of rebar sticking out of this wall instead of two. One would be the one that would engage the wall here, and I put this here to show it's the sheet piling. In reality, it would just look like almost just like a straight piece of piling off. It would look like probably more like this from a side profile, and we wouldn't be able to tell the depth of it. So that's the sheet piling, and then the concrete wall, the block reinforced poured wall, reinforced. It's a difference between this wall. I think this is, I don't know if that's 12 inches or it's 8 inches. The thickness of it matters sort of about this ledger. It appears to represent more like 8 inches based on the 8-inch block above. And it appears that that the slab detail might actually stop a little bit like that. Okay, so we have these 90s that are supposed to have been engaged from the slab at the end here. Not to be confused, this slab detail, let's turn to the right a little bit. Looking at the drawings, it looks like that. So here's the top of the wall. We're looking down as a bird's eye view. And these are these 90s, spaced 12 inch on center. Although I did find somewhere else it said 13 inches. But 12 inch on center. It also stated, if you recall in the drawings, put number 4 rebar at the bottom, 12 inch on center, both directions. But the problem is it did it like a note. And it looked like I could find 4 points on the drawing where it mentions that. It's not like it's a tough call. But with that said, I look at the imagery from one of the helicopter scenes, and I do see underneath the parking garage area, it is 2 directions. It's not disputable with me. It's 2 directions. I will go down another trap video on that one, meaning fall into the trap, the hole of it, because we see that I can see this 2 directions because the rebar is exposed in 2 directions. And at the same token, I can see rebar ripped out of the ceiling in 1 direction. I can explain that. It'll be in another video. It will tell you about the reinforcement. So just because we know there's 2 directions over here of reinforcement, because when they pull the samples out of the ground, we saw the 2 directional samples when they did the cuts. Some of it niched through into the air, into the winds, throwing it away. Let's see if I can show you the general setup here. This is deflection. This represents stirrups, where each one of the columns would be. You would have stirrups here also. I want to do a video that shows some of my details up here. Let's see if I can zoom up a little bit. I don't want to do this one yet because I'm not ready for it yet for you guys. But that's a quick little scan at it, and I'm going to show you how this is a crank bar system and how the stirrups work together. In other words, I'm just going to lay out some steel. It's going to be real simple. Imagine me just laying out steel here with no concrete, and then you apply the load in the center. Well, you're going to have this piece of steel, and you apply the load, and the steel's here. You apply the load on. Well, that's no steel. The steel's here. The top steel is this red line. Okay, so it's this red line right there, and the red line there. It goes across the heads. It's the steel that holds it from deflecting downwards. I call it the negative steel, to stop it from pulling, to act in a cantilever capacity to help do the supports. The general rule, it's real simple. It's just 25% in from the span, and those spans have a limit also. The concrete thickness is relevant. Let me tap the screen and get you a better focus. And same thing over here, just about a general rule, 25% is going to get you there. And then the other one has to, of course, overlap. You can run that all the way through. The bottom one, the bottom steel, you can run it all the way through and connect. So if it does start to deflect, it still has to pull on these 90s coming out of here, anchored here, but they are a 90. So it's still got concrete to work on. Now I want to use this ruler, and I want you to visualize this, the column and column. I'm going to put the concrete here now. I want you to visualize this just dropping down as people want me to. You can see the arc it creates. At one point when it breaks free, it's got an arc. It's no longer going to be at that building here, contacting the building. But look at, to do that though, observe my right hand, now the right hand, what had to happen. This huge cantilever effect had to take place. It had to raise that up. Without raising it up, and you have this rotate down, without raising it here, you create a stress here that would cause a fracture. Well, as we know in the images, it would cause a fracture to burst the decking through, because this is pinned at this point. This doesn't have the ability to go that direction. If that's pinned, as I just stated, with the rebar, then the rebar should be bent in this capacity. So it had a moment where it was pushed back. So we should show it like that, exaggerating a bit. But to do that, to push it back, it's not for free. It would have to push all the way into the building, because you can't just push one without the other unless you can create a drape, a sagging in the center. I'm trying to focus. Hold on. It's a whiteboard. I got to go on the angle of it, I think. It can't find depth. Okay. So the rebar looks like that, but our rebar looks like this from out of the column heads. And I believe that's because the rebar that was there, when it was stripped off, it bent this rebar reinforcement over, spalling the concrete off here in this zone. Here, I'm looking through the camera, so bear with me if it doesn't look that great. Spalling it there. So it's hard for me to get the rotation there without looking for the first issue, would be the first column. This is the one that would be indicating that this moment took place. Or we would get looking from the top down. So let me take some liberty here. Looking from the top down the deck, we have a column here. Let's say column here. Let's just draw a wall here. When it's split, if this side went down first, it all went down together. We'd want to see a split across here as the cantilever point, as the hinge point. You can put it in front of the columns if you like, but I don't, looking at all the images left and right, I don't see the split there. All right. What we do see there, though, is a little further over, we see a split, if you will, but it's in this capacity and a butterfly capacity going up. I'm exaggerating exaggerating that. That's also biasly so because confirmation bias, because there's a driveway there, allowed it to fall down further. If I put cars in there and I only allow it to fall that much, now it's still, then I still try to evaluate. I'm still back to evaluating this first column, the first column, to figure out its interaction with the outer wall. So the issue here that I see is that we do get deflection here, but remember there's vehicles here and you can bring it over towards the pool. Using the vehicle location, we were getting a deflection, loading deflection, right? They took a bunch of surveys. They took a survey of this property, this lot. When they took the survey, did they have everybody come off, or are they guesstimating when they did that survey? I would like to see the video of that survey, considering that the deck had cameras working at that point, right? I mean, it seems like they never had cameras working. And would they have recorded the tapes? Recorded it. But kept the recording. But it's interesting that profiling deck, was it loaded or not loaded? That is important. How about loading and unloading on it? I just did the video talking about that, the convoy, the Freedom Convoy, if you will, and they loaded that bridge, the Ambassador Bridge, with tractor trailers. Not all of them full, But that's a nice load test of that structure from one end to the other, wide, both widths, both from wall to wall, outside to outside. That was a nice load test. Now they should go back there and check the structure out, because it was significantly loaded now, that like it's never been loaded probably before. I don't know if it's ever been loaded with just tractor trailers front to back, ever. Now, okay, so the steel here at the bottom stops it from deflecting down. The bottom steel, it looks like this. Let's just do a little thing like that. But it can't deform like that without pulling on the deck, the reinforcement here. It just can't happen. It can't displace unless you've got cracks in your concrete. Okay, so remember the top reinforcement and the lower reinforcement without any concrete on them at all. I can clearly just bend this rebar here and here. Once I engage the concrete and it locks in, any pushing of this one also engages this one. They're acting together. Okay, to keep them from separating, you use stirrups. And now, just like I showed you in the tree video talking about stirrups and trees, this keeps it from blowing out. It's like a glass, a cup of water, a plastic cup you load with liquids. It's not a balloon. It won't open up. It's limited, confined by its ability by the steel. In this case, I don't believe they use stirrups, so stirrups don't exist in this system. They didn't use crank bars like this little design here where you come over and you come up and over. It stops shearing with this detail here. So they didn't use crank bars. So they just used layers of steel. And what holds it together now is the concrete bonding strength in PSI. So PSI, say 40, let's just round up that this came to 5,000 PSI. Tension-wise, it's going to want to separate around 500 PSI. Not much PSI. Okay, oh, wait a minute. We have core samples, rebar. We have core samples that look sort of like this. And oddly, maybe like a tooth here. No concrete here. It's already been vanished. Pulverized. Okay, so now you can pulverize something and make it much smaller dimensionally. For example, using the cat food as a additive to get the cats to eat the raw meat initially. I took a huge huge bowl of the dry nuggets, and I ground them. When I was done, I had 3 pill bottles. The 3 pill bottles easily fits into this giant bowl I had. But, so the same thing here. Okay, so let's just do that to remind you of what's going on here. Is that this sort of looks like the rebar, the core sample, and then another section of core sample. And I will not count the top deck. It wasn't tied together. But you get this deflection, and because the deflection doesn't have stirrups holding it together, no stirrups here holding this together, you do get separation. This is how I can explain the separation of the core samples from the top concrete sample to the lower concrete sample, if you will. That the dissection took place because of the deck deflecting under dead load, and no stirrups binding them, marrying these two together, giving it increased tensile strength in this capacity. So our deflection creates a shear plane pushing this way, pushing that way, right? The deflection down, you get bypass. So this is how I say that, because this side is in compression, the top side. The other side's in tension going that way. So you can see why we're getting 2 planes. So this way, that way, and then we'll put 2 arrows pointing inwards for you guys here. So that's doing that, that one's doing that. And our shear plane is divided in the middle by the reinforcement. In this case, the bottom reinforcement. We only have it at the bottom. So if we do that a few cycles, can we get the deck shearing over here with the reinforcement in? Well, yes. If you can get a sample over there that looks like the sample that was over here to the far right at the LMN location, then you could get this breaking down. But remember, we have an identified fracture that lines up with the cars going all the way over with the planter box. Can we use the planter box as our loading point along with the cars? Cars being here. So let's get rid of this deflection. Now let's do an overlay. Let's do an overlay. Let's leave it there and just do a car. So our cars are here. All right, so our vehicles are here. And then it's on this side of the column, planter box, and then on the other side is the other one. We'll just deal with this side, since this is the side that's of most interest right now. Here's our fracture plane. It's also where our planter boxes are, though. Planter boxes are back here also. So we got a significant weight there, a dead load that's always there. Always stressing here. Now, I'm not one to believe. I know how to do the calculations, but I don't quite believe it. I'm not a salesman on it. Let me tell you the part that I'm driving at in a second. I'm trying to get the screen to focus. Okay, maybe that will hold. I guess I'll turn on the light. Hold on. Let me give this a little more light if that works. Sorry, just flipped over my weights, hit my weights in the bare toe the other day too. Keep them handy. All right, here we go. So I'm not one to believe that when you divide a load up, here's the column, here's the wall, and you take half of this and you put it on this column, you take half and put it on this column. Well, I don't believe that's true, all right? Because if I remove this half, if I'm allowed to do that, if I remove this half, this puts this in cantilever from this structure. If you told me I'm supposed to break it in half, if that's the case, it would create this cantilever, and this would want to fall down here. It would want to rotate down here, prying this up, prying this section up. So I don't like the halves. And then when do I stop with the half? Shouldn't I go another half on this loading now? Should I say, okay, how's this handled? Okay, well, this half is handled here. This half is handled in the mid-span. Oh, wait a minute. So then that would be half there. So this is handled by itself in the middle. That middle is the part that's stressing on the two ends. That's the way I see it. Yes, you can get some ledge. And this is provable and proven if you look at the failure of the structure over there at the Champlain South on the wall. We see that many fractures happen, but we see it sheared off at the wall. I mean, it's right at the wall at each floor. There's only one, I believe, that just flapped over. So it broke here and then flapped over and is hanging with the rebar against the wall. But the rest, they didn't even give us a little cantilever. You know, out there to this 25% rule. They went out, they were shearing all at the wall. All at the wall. So much for being able to resist. It didn't even hold up and say, you know what, I got it from here and break at this point. No, it broke all the way at the wall. I'm really not a believer that you can a cantilever, yes. This is not a cantilever I'm referencing. I'm referencing trying to calculate the loads of a structure by the acceptable engineering form of using, just dividing the span in half and throwing it on this one half and then throwing it on this half and calculating this column by these loads, not by it crossing the line and going all the way over to here and then overlapping down to here. Not even doing 3/4. Not even. And then we have the negative steel. Remember, if I do this, this will want to just flip off because there's nothing. So if I were to remove that, this would just flip off. So you need that something to anchor it down in here, or a counterweight of it over here. Okay, I got to go a little more to the right. Or counterweight of it to make it like a little capital, a little balancing beam. So I don't like I'm not hard set in believing that half the load goes over there. That's also similar to this. Let me show you one more time on this. So let's do this to prove what I'm stating. Here's your column. Let's call this a halfway point. So there had to prove that what I'm saying is correct, and no one's going to dispute this part. No engineer will dispute it. Okay, half the load goes there and half goes there. All right, great. 40 pounds a square foot. I put a refrigerator right here and my whole kitchen setup, my stove, my dishwasher, my sink, a standing person. Oh, it's fair because it's the same load here as if I move them here, and as if I move them here, and as if I move them here, and the standing. Well, we know that once you look at it like this, and that's not true. It's creating a huge bending action, and a lot of stress here, uplift, etc. If I move them over there, then it's more direct down into the column. If I move them out here, now it's almost direct. It's got a little shear action going on right here, but it's pretty much direct back to the column. As I move further out, I move into this problem. And that's why I just don't like the general formula of, oh, you know what, it's half over here, half there. That's not true, because now with this in mind, now I want you to put the car, so think of this over to the left. Now we got a planter box, and then our car is out here. Now you can see where the loads are jumping over. It's the dead loads that count and where they're located, not just the dead loads and divided up. It's where they're located. Just like this would matter, that would matter. You got it. The point load is what we know about. But when we get to this calculations, all of a sudden we just sort of throw point loads out the window. And we just start doing that and then start adding in the dead load requirement and then the live load requirement and dividing it up. But in reality, we're forgetting it's point loaded also. This is a point loaded system. It is point loaded with the vehicles. So coming back to the question is, how do we get this to fail here? Well, I could come up with a fracture there. We could come up with it that if he had a core sample, and so this should be extrapolating and reaching, because I don't have a core sample over here. And I would be biasly so stating that, let's say it looks like that over here also. I could kind of argue it saying, well, it was near a strong point that this shear plane took place. It was by the columns, if we recall. The column was here, this is 11, and the core sample was out here. So it was by somewhere where there was deflection should have been very minimum. It should have been one of the least minimum places to find this. But yet it was found by the column M. If it's found there so closely, why can't I state it's also found over by the wall there? You know, I don't want you to dig your heels in on this one. This is not the hill to die on. It's just something that I told you I try to debunk myself, and I try to support. Now, for code word existing code word for someone, I don't see the top steel. I use this as my bias point. Also realize I have a bias to want to find it over there with the data that was presented to me about, because you guys remember months ago someone got hold of me that will remain anonymous that was at that location and made it clear that they saw no reinforcement coming out of that wall. Or let's say no, meaning pretty much insignificant. How about that? Meaning apparently there is steel coming out of the wall, but the person alluded to that the steel was minimum, very minimum. How about that? And if they want to speak up in a forum and identify themselves and give more details, they sure can. But you got to be careful, because these people will dox you, and next thing you know, you're in a court. So here's your 90, and there's your rebar this direction. The 90 here would engage this deck, but it acted like a no uplift requirement there. It's like that they didn't care about uplift here at the end with this on it. We saw it go through a hurricane. We've seen this wall fall down. Okay, so that's for the Washington Post guy that got hold of me about that. That's the hurricane wall that fell down. It does not have any anchorage in it, so it shows it's a hollow block wall that was sitting on top of this system that blew down for whatever reason, however the wind forces got hold of it. They then pull the permit and they put the wall back on it. It would be lovely to see if the imagery of that. They also added planter boxes, removed planter boxes. Again, there's no top steel that I could observe over there. I keep seeing one piece of steel. It appears to be located more towards the bottom. The bottom steel in this span would be taking care of the tension part. It typically would not. It's just not a one-off in that span. You're going to need some top steel. Over here it's present. We see it. I call them the antennas. The antennas run the antennas when I do the video. So here's the column. We're looking at it, right? And this is the back wall. Let's put this is the back wall. And I'll put the column too close, right? So you guys. So here's the column. Our antennas are running this direction. The cross steel of this. I do not see any antennas running two directions. Doesn't mean they don't exist. They could have flapped over and went down with the deck. All right, the two of them, when it punched through, it could have moved over. You know, they could have sized it like that where it just slipped off. Why do I say that? Slipping off and going that way? Because we have, at one of these locations, this is the side profile of it, the antenna's bent down like that. I show that by the pool deck where I can show you the antenna across it still and stressing this rebar, meaning it giving it its work to be able to pull it, its contact to show that it can pull over the rebar and spall it. That's literally by the pool. When the firemen are there, you can literally see that rebar there. So we have this going this direction, not there. That would be the top steel. This steel here that I refer to, this right here. That's your top steel. Over here, I do not see the top steel. Let me just put it in there. So that would be, let's call that top steel, and I went right over to there roughly. And then that red line, this red line and that red line represents the thickness of the concrete, not the scale, of course. So I don't see stirrups, so that would allow it to allow it to fraction come through. No stirrups over here, allow it to fracture and come through in this deck. Now, you wouldn't do stirrups in a deck like this. You would do more this cant strip design, like this. So it would be more like, that would be part of the top steel. Oh, that's a 45. And then the bottom steel would come all the way over too, also. And that's your top steel here, and it would come over and then turn down. That's your and it's all the way down the length of the deck. That's your shear protection. Sorry, I'm trying to draw it as through a camera. Okay, so you can imagine how fun that is. So I have my loads. I have where the loads would want to stress the deck there, using the person and telling you about load and point loading, etc. Point loading counts. Clearly, this should count as a point load. Whether you like to say it's temporary or not, well, that's just your amygdala arguing that it's not a point load because you drive it off. Okay, it's mostly on, and it's there, and it stays there. At what point is a point load no longer a live load? Or what point is a live load become a point load? You know, they can be people, you're just playing with it when you're arguing that a refrigerator is not a dead load. You're arguing when you're saying microwave's a dead load. You can move it around the kitchen though, so it's kind of weird. Oven's a dead load. A dishwasher in its location becomes a dead load. All right, it may move, and you may be able to move it and design your kitchen differently, but it's a dead load at that point, so it's a point load. So this is a dead load. And live loads are just dead loads that move around. All right, so how's that? You know, live load, many humans. We're just dead loads that move around. We create a lot of point loads everywhere we move. And so getting back to this, this is kind of a deep video about this, trying to help you understand it. But this is how we could get, if this was over here, the point loads here could cause a fracture, dipping here first. So that could dip first, right? Let's do that. Now, once you do that, you now have it pulling away. So here's a pulling away action. So it's pivoting from here and here. It's pivoting away. And once it pivots, it's pulling also. And now it's going to drape and pull down. I'm sorry, now it's got stress over here. So it's going to want to pull down. At that point, it finds, see the end of the pen? It finds equilibrium and pushes the red cap back into the wall and pins it against the wall. That's how I can get the jealous wall to now get its attention. And that's why it's always been called the jealous wall by me. I knew that I was going to have to talk about this. I knew I was going to have to talk about this and get to it from there. But I don't have this as the starting point. I have this as our starting point of all our failures. The deck. And not having stirrups, not having crank strip design, crank bar design, not having a stirrup detail. This is representing a stirrup detail failure, if you will. They're coming apart. Remember what I stated, that if I just show you the rebar here and the rebar here and I don't tie them together, what happens when you push on this rebar? Nothing. But if I put concrete between them and I push on the top rebar, loading it, I'm now pushing on the bottom rebar. But when they displace, they're going to want to create a shear plane. The rebar is right at its own literal concrete and fracture it. As many people point out, not many of the rebar looks rusted there. Right, and so how do you get the fractures? Well, by shear plane, by movement, by sheer span of it. And we can then biasly so, confirmation bias, talk about the BMA that was supposed to be in here. It's because there's no BMA, this stresses the whole deck area differently because of this point loading. This dead load, point load, whatever you happy with. You know how I see things differently. And it's a magnetic board. I was going to use paper to try to do it, but then I realized I could use this by perspective, by moving it in to the camera and show you the pin against there, the pinning action, and I can rotate it and you won't know that I'm actually doing that. And so we start here. It goes down, it deflects right there. It pulls down, start punching through. And as it goes down, it can't go any further. It pins it against the wall. Keep in mind, the red tile on this slab is pinned against the wall too. So it's showing a good clear plane break there. And remember that this might look like this. With that said, then, the pulling action, the popping action, here's the debunking part. So the popping action, I've taken apart many bolts and rebar and made them fail. To make rebar fail, hold on. Okay. To make a nut or rebar fail, hold on. Got it right behind me. This is a concrete rebar pull-out test. And this sample I was going to do a video of you for. It's right where the clamping mechanism is, elongation and stretching. So right here is where it broke. This is rebar. This is going to be put under a microscope for you guys. And I'm going to talk to you about how the molecules compress and some stretch, elongate in the bar itself. And you'll see the density increase. And some of it won't increase. So the failure is actually in the brittle part, not in the soft part. And the brittle part is where we get our hard part. Our hardening is where we get our abrupt fracture. Let's see here. So over here at the wall, so debunking my statement, at the wall we have what appears to be the rebar broken in plane all the way across. So that implies that the concrete, just like this clamp, was holding on pretty close to the wall. And it took the stresses and then fractured. It fractured. Now, see my rotation there? It's not for free. Look at the bottom of this and watch me rotate. As I rotate, if I just rotate, I'm going into the wall system. So right about here, we should see damaged wall. We do see that damaged wall, and then where you see the wall dip down like this, and you see wall missing, that indicates that the deck rotated in position from out here to the right and pushed into the wall, calling that spalling of the concrete off. I know it looks like some of it, when it's ripped down, they could have caused it also. But you have a combination of them both, rip down and rotation in. It's holding on, and then it spalls it off, and at one point it fractures it and breaks free. You would have to grab that rebar, take it out of that concrete, clamp it, and do a tension test on it to see what would cause that rebar to fail. And people want to know about that rebar. You simply take it out, cut it, get your lengths, and test it. Now, I saw that they're requiring 3-foot lengths. You definitely don't need 3-foot lengths to do rebar testing. It's going to be stressed. I can test this bar again if I wanted to. You do not require 3-foot lengths to test rebar. You can do it within inches. All right, rebar doesn't state 60,000 psi with 3 foot of rebar. It's 40,000 psi rebar with 3 foot of rebar. No, the whole bar is 40,000 anywhere you pick it, and it's funny, I'm gonna be trying to debunk myself where I said anywhere I pick it already. I'm like, okay, I picked the very end, and there's nothing there. But then you're not on a rebar anymore, are you? So so the rotation at one point pops off. How can you do that if you're not connected? It would want to pop off where it's connected at. So over here at the wall, we have a connection that popped. Now I try to do things like use the bottom of the concrete as the shearing plane, and I just don't have that concrete having the ability to shear it off. What I've done before is wedged in here to see what would happen if I elongate concrete with a wedge in here. Would I create a fracture spalling in here? No, it just fractured the rebar faster. In fact, when you pull it, when you load test it on an angle, it just fractured it faster because it's not pulling all it. It's pulling on it on a 90 on an angle. So part of the steel is in compression, part in tension, and all it cares about is knocking out the tension part of it. And it can do that a lot easier when some of the steel is in compression, meaning rotated. So as you rotate, you now got less tension ability in it, and it can pop easier. That's the end of the video. This gets pretty complicated when I start going down that line, doesn't it? I'd like you to think about this, though. You're going to have to go over this video a couple times. It's 37 minutes long, so I got to shut it down now. All right, love you guys. Bye.